I will demonstrate on the water you collected in the Chernobyl site. But first, water fractionation. The important to remember and to be aware of is that total concentrations is information and it should be measured, but that gives no information about processes and mobility and bioavailability. So just to measure total concentrations, whether it's in soil or biota or water, it's not giving the enough information to estimate risk, to consider countermeasures and so on. It just gives a number, but it doesn't tell how the behavior of the radionuclides can be in the environment. So we need to do more. For water, we do ultrafiltration, and that's a way to fractionate water into different size. And we also, when we have ultrafiltrated water sample, we put it into some ion exchange resins to also fractionate on charge, because that will give you more information when you both have the size of the radionuclides, what size they are connected to, and also what charge they are connected to. You have probably seen this picture before somehow in this course. It tells what sizes we put the sample into. We split between particles, and particles are considered to be the fraction higher than 0.45 micrometer. So then we use filters to do that. In practice, that means we take the total sample, we put a filter, and then what's coming out in the other end of the filter is 0.45 micrometer fraction. There are a lot of different filters that can be used. You have probably seen this before. They are okay with very small samples, but you know the surface of this filter is not many square centimeters, and you press the whole sample through the filter. So when you have a short or a very small area here, press the whole sample through. It's very easy to clog or even to destroy the filter, because you use force to press the water through a very small area. For small samples it's okay, but for bigger samples you need bigger filters. I have a membrane filter here that is much used. It can be put into a housing like this, but it's the same problem here. It's a small area, just a few square centimeters, and you need to force the sample through somehow, and then it's easy to clog the pores, and then you don't necessarily have the 0.45 micrometer cutoff anymore. Or if you put even more effort to have the sample through, you can destroy the filter, and then you destroy your sample. You have to start again. We prefer to use some housing filters that is meant for one-time use. They doesn't look too big, but they have a much bigger area than the small filters. This filter has an area of 3 square meters. So we prefer that for bigger samples, but if we have even bigger samples, or we go out in the field to really sample big volumes, this filter, even almost the same size, has a square meter of 7 inside. So it's almost a room inside this housing. So that gives us the opportunity to filter a big sample. And even though it's a big sample, this will probably not be clogged because it will be so huge area to fill up with particles. That was 0.45 micrometer filtration, but then we pressure the whole sample through, and what's coming out on the other end of the membrane will be the smaller than 0.45 micrometer fraction. To split between the high molecular mass fraction and the low molecular mass fraction, we use ultrafilter. You see the setup here. It's actually a figure of this one here. So we have a pump. We go out in the field and pump the water through the 0.45 micrometer filter. But before we do that, we prefer to have a 4 filter to just remove plant parts and whatever that could be in the water. So we use this small nylon filter. You can almost see the force here because you can just send it around. So it's a big filter when you if you look at the 0.45, this is much bigger, so it will not remove particles that you are interested in. It will just remove different things we don't want in the total sample. So it could be that if it's a lot of plant parts and so on in the total water, we would like to filtrate with this 100 micrometer filter even before we do the total sampling.
Okay, but in the end you put them together to measure, because it is 2 parts of one sample, no? The filter this and smaller filter.
No, yes, this is just a 4 filter.
Okay.
It's just to remove big particles that has nothing to do with radionuclides.
Okay.
If it's plant parts or big small stones in the sample or whatever,
Okay.
we don't want that in the sample. We don't want that into our instruments. But it has nothing to do with radionuclide or particles or something. So we prefer to use this just to protect the other filters and the instrumentation later.
Yeah.
So it's just a 4 filter. But this is the 0.45 or these others to remove the particles from the water sample. We can keep on with the hollow fiber. There are a lot of different systems for ultrafiltration, but this is a hollow fiber for ultrafiltration. That means it's a filter with a lot of tubes inside. I don't know if you can see that. It's a small filter. You see all the tubes? Yeah. And this is a very small one that you normally just use in the lab because it can't take that much sample at a time. But we normally use a much bigger one out in field. That can maybe give half a liter per minute or something in sampling. This just gives too little in field. The principle of the hollow fiber is that you have these fibers. This is a little bigger, but still it looks like this. And it's a lot of hollows in the walls, like this, all over the tubes. And the advantage of this filter contra others ultra filters, where you press the whole sample through, like you do with the 0.45, or use centrifugation forces or something to press the sample through a membrane. In this case, the whole sample goes through the tube, the big hole of the tube, and the filtrated water is going through these small holes in the tubes. So all the time you have the sample just going through. It's not pressed, the whole sample is not pressed through the filter. And then you avoid clogging, and that the pores will be closed. So you're actually washing the filter all the time as you are sampling, and that you avoid that you have the wrong size of the fractionated water coming through. So it's a very good system when it comes to this clogging of the filter. And that's a main difference between a filter where you press the whole sample through, and then you will of course have clogging and filling in the pores, and then destroying the cutoff. In this system, you avoid most of that. If we do the next picture, it's a question about should we do the water sampling in situ, out in the field, or in the lab? And the answer to that is to do it out in the field, if possible. It should be done out in the field. Why do we do that? It's because both the physical and the chemical properties will be different over time. It will be differences if you take the sample out in the field, bring it back in a bottle, and do the filtration in the lab the day after or the week after. So the best is to do it out in the field, in the river, in the water lake, and to have as short time as possible from the sampling to the filtration, and then even to the ion exchange. So we bring the whole system into the lab, into the field. It's not that convenient to do that because we need to bring the pumps for the bigger filters. We need bigger pumps because we need a certain flow through the filter to avoid this clogging, and we need electric power. But even though it's so much better to bring it out in the field, to bring the sample out in the field. If you work in estuaries or some other systems where different water quality meets, that will, in the meeting points, you will have chemistry that is very changeable due to pH or due to. And if you remember, we said yesterday that you should acidify the sample out in the field. But if you bring sample into the lab to fractionate, you can't do that in the field. And then of course you will have wall problems in the sample when you bring it into the lab. So, and even, especially now with this really high pH in the sample, you will have even more problems with wall effects. So, when we filtrate this water, probably we will lose something that is stick to the walls of the bottle. But we can't acidify before we do this, because then we destroy the classification in the different fractions. So it's again, it should be done in the field. We don't bother to measure the pH and so on now, and the total sampling is just to take the sample from the bottle, maybe through the pore filter, and into a bottle. We did that yesterday, and then I just remove this one now, but it can still be there, the pore filter for the next filter, but then it's a 0.45 filter. It has a flow direction, and that's important if you're using these housing filters. So it's an arrow here saying flow, so I put it in the correct flow direction. now connected, but it's not going anything out of the filter, because for that we need some to change the pressure. So the sample will now just go through this filter and through the tubes, and then we can collect the 0.45 fraction. Oh shit! Something happened.
Yeah, this
These
tube.
lines that I think we should close this. And I think the speed was a little bit high. So this is now the fraction that is less than 0.45 micrometer. The whole sample is going through the filter, and all the particles is left to the filter. So you don't need to do that for the whole sample.
So you use two filters. One.
Yes, but as I said, this sample is just going through this one. It's just to avoid to connect and disconnect it.
Okay, it doesn't collect.
No, it doesn't connect anything.
Okay.
So it's just going through these tubes.
Yeah.
Nothing happens.
Mm.
Okay? So it can be put on even when you sample the other fraction.
Mm. Just protect pump from damages or something.
Yeah. But if I am to take a big sample of this one, I will disconnect here maybe.
Okay.
But you don't have to do it. So when we have collected the 0.45 fraction, we would like to start with the ultrafiltration. Then you saw that it was a lot of sample pumping through at the time. So to make sure we don't use all the water, just easy. We put the sample back into the bottle and have a circle. We recirculate the sample, but that's okay if we have taken out all other samples from the bottle that we need. You need to take the total first. Well, and we'll need to measure pH and conductivity and take out the sample for total organic carbon before we do this. And then we take the 0.45 sample. If we don't do that, we will kind of destroy the other samples, because now we will change the sample in the bottle when we put it on recirculation. Because we remove some of the sample in the ultrafilter, and at the same time we up concentrate this one. So make sure if you are doing this kind of ultrafiltration to do all the other sampling first. Then we can start up. Yeah, but it's not coming yet, because as you see, there is no sample coming through the tube, even though the sample is going through the system here, because we need to put on pressure against the water flow to press the low molecular mass fraction out in this tube. Because now the sample is just going through the tubes, and we want it to go through the small pores. So we put a little pressure here, just to squeeze and I have measured the pressure here to make sure it's not too big, because I don't want to destroy the filter. So now you see this filter is very small and it's getting slow. But you see the sample is coming up now. Anions and room for cations. We have found these to be okay, but there are a lot of different ion exchange resins. So you just need to pick one and to see if that is a good one for your purposes. This is a strong anion and a strong cation resin. So you just add that to a column, and we take from the less than 10 kilodalton fraction. We have nothing there, so I'll just trick a little bit here. And because I just have one pump, I need to change this one. So I take from the less than 10 kilodalton fraction, and as soon as I've made enough sample of that one, I will start with an exchange to make sure it's not too long time from the sampling of the ultrafiltrated fraction until I put it on the column. I need much lower speed. And then I just take it through the column, and this is an anion exchanger. So the anions in the sample will stick to the resin because the resin has a surface filled up with chloride minus, and the chloride minus will be released and some other anions will get stuck to the resin. And then we will have chloride in the sample, but that doesn't matter to us. Stable chloride. So what's stuck in the column is the anions in the sample. And